good papers, especially the factor artifact, artificial neural network user. It was very excellent. I'm a student from Nakhchivan State University, Azerbaijan. My work is, 1 minute. Okay. My work is natural language processing. I have used Tolstoy as an object of study. He was a great poet, and he has affected the Russian people the most than anybody else in their history. What you can see in here, this is I think my paper includes all of the introduction, and I had very less time to prepare the presentation, so I hope you would enjoy it. There's the Toy code. You can read all of the paper. I thank my mother and especially Dr. Andrei Karpady, University. He's a professor of University of Stanford, and I have seen his manuscripts who suggest very good options for modern NLP architectures. These are topics, and this presentation covers an image of an artificial neural process from it's end-to-end processing of all of the steps from biological perspective to the supercomputers at the end. Architecture. So these are the required steps to build a NLP software. Mathematics, probability, statistics, machine learning, even deployment is in here. Feature engineering is very important in deep neural networks. These are the mathematics areas required for building this. These are the mathematical areas: probability, calculus, real analysis. Statistics libraries are all including these. And we will be using deep learning because NLP, we won't be using classical NLP. We will be using NLP using transformer architecture. We have deep learning all inside the other areas, especially machine learning and history. We can see the Asimov in here in the picture. Asimov has had 3 rules. He said it has a very important 3 rules. I think we have talked about AI ethics in the previously from this conference. And Asimov had 3 rules. He has outlined that robot must first obey the implementer, the person. It must not exceed his rules. Those are very important rules. And we are actually in the narrow AI, and we are going towards general AI. It's proposed to be in the 2050s, and it's also called future AI. But everything now we got is narrow AI, and we have broad AI also in some applications of Tesla machines. At the bottom of the artificial neural networks, it comes. Artificial intelligence, machine learning, we have classical models, and then we have neural networks, single layer neural networks, and we have deep learning, multi-layer neural networks, and those neural networks rely on biology. And this is a human biology. We have, if you see temporal lobes, frontal lobes, all parts of these are simulated in the artificial neural networks. Those are called artificial intelligence. If you see, we can visualize something like that. We have tons of billions of biological neurons in our brain, and if we graph it, actually, artificial neural networks is a graph. It's a matrix. We can call it graph very clearly. It looks like this sample simulation of a biological neuron. We see the propagation of the electrochemical signals. This is the structure of the biological neuron. We have the cell body, nucleus, dendrites, the axons, and this picture in the top right, this is a real picture of a biological neuron. If you see, and we have billions of those biological neurons. This is another picture. We have a myelin state that covers axons of nerves and helps speed neural impulses. And we have another simulation, and this picture shows the electrochemical propagation of energy from a center of one neuron to another neurons using the axon terminals. This is a very important picture. So the left side is the biological neuron, and the right side is the artificial visualized abstracted model of the biological neuron called artificial neuron. And this is another history table of artificial neural networks. And we see the perceptron from 1957, multi-layer perceptron, SVMs, and deep neural network from the 26. Another picture, we have the activation function, transfer function, or use it. And again, this left side and right are very similar. This is another transfer function, and we pass the transfer function summation into the activation function. That is pass it to the next neuron, artificial neuron, and these are the. I can't skip this part. I don't see the top of the screen. Okay. This is a convolution neural network. This is based on lots of layers. Those are called convolutions. This is the title of the deep learning, and we have used transfer architecture, but the convolution neural network is very important for computer vision problems. Structure of a neuron. I have lots of these slides, and this is very important phase. In the machine learning tradition, we had extracted features by hand, and they were classical statistical libraries like algorithms like decision random forest classification. But in deep learning, we have everything inside hidden layers. There's no feature extraction. It's all done by computer learning. Feature extraction, you see this German visualization, it's good. Everything is done by the deep learning architecture. This is another one layer, one hidden layer architecture. Another, and this is an important graph because we have now outlined this that we have now we had reinforcement learning. That's very important, very strong tool, and we have now the deep learning added to reinforcement called deep reinforcement learning at the end, and we also have deep Q learning. That's also very important, and it goes on. Now we have foundation models. It's based on transformer architecture. We will explore in this paper. Feature extraction. It's another page showing that. Okay. And this is what is called feature extraction. We take a car, it's actually in the deep neural networks. We take a car, we add new layers, and we learn different features in each of those layers. For example, the first hidden layer learns the patterns, the second one learns the objects, the third one learns the hash map of the image. And NLP, natural language processing, it was earlier classical. We were doing the lexical, syntactical, analogy, all of them from the data scientists. It was extracting the features. It was finding the best validated result. But now everything is in the deep learning. It learns the features. It optimizes it. Everything is done in the deep learning hidden layers. And if you see sentiment classification, entity extraction, which are nouns, translation, all are used, and emotion extraction, all of them are done easily in the hidden layers of the deep learning. And you see this, there were conditional statements in the artificial intelligence earlier models, and we have machine learning is statistical algorithms, and then single layer artificial neural, and we have multiple layer deep learning. Another history table, we had a dark era where the computer processing, and we also had a winter. It is called winter, AI winter, because it was the area. I think it is in here, but it's not in here. There is an area. The computing processing power was not good enough. I think it was in 1970, 80 to 80 up to 80. The computing processing power was very low, so they have skipped the funding to the artificial intelligence because of the computer processing power was very low to build artificial intelligence models, and single layer, multi-layer. See another, and if you see performance traditional machine learning with statistical algorithms and neural networks and deep learning, multi-layer neural networks and neural deep learning architectures. Another picture of feature extraction. If you see different actually those are the pictures. The features, different part of the images are learned. We have deep neural network, convolution, and we have recurrent neural. Actually, those RNNs are not much used now because we have transformer architecture much better than that. RNN architecture and CNN, but it's still used. We have vision transformers. It's going to, I guess, it's going to replace it somehow. We have classical reinforcement added with the classical deep learning. It's become deep reinforcement learning. That's very strong tool at the moment. And applications of deep neural networks in object recognition, speech recognition, vision problems, and even the cancer detection. All are vision problems. And this is our paper. We have studied Tolstoy, and these are the I have taken this by word clouds library. the point of Tolstoy's works are people. If you see, it has encountered the people word 1,021 times during the learning, and Tolstoy's objective was people. This is our architecture system context diagram. If you see, I can zoom it, I guess. We get artificial intelligence deep learning, and we also keep in account the architectural points. We use PyTorch or we use TensorFlow. We have 6 sequential transformer block, encoding text, activation function, going forward, token generation, decoding per mapping, and encoding and decoding. We have decoder and encoder both because we have a generation model. Optimizing this, I have used cross-entropy loss estimation. And at the end, it's going and it's learning itself, feed forward and back propagation. This is a loop, right here. And we have also looked at our fitting issue. We have graphs taken for that. And I've taken 90,000 all works from this book. It was after pre-processing, it was 90,000 of lines of raw text, all Tolstoy's works, and we have split it into entities and then tokens. These are the stack of including them. The thing is, we take the after architecture here, I'll talk about it. We take the probability distribution. It determines which word would come after that. And this is the loss validation, loss training, loss matplotlib. And if you see, this is good learning. But I couldn't decrease it below 1.5 at the end. This is a step. We're passing the through an empty tensor 0, 0, iterating over the number of requested token size, and the token size value is 8, and getting the current tensor of empty and active length word size. It's from its tail, yeah, from at the end of the generated sequence, and passing the callable class callable because NN model we have used PyTorch's neural network model. It has there's a callable method. It turns off the largest and the last tensors, take largest and fill in softmax function. Yeah, we get the probability vectors. That's done by the softmax function because it's at the output layer, at the last layer of the neural networks, and we take the character from multi-node probability distribution, and that tells us that this word is best fit after this word. For example, from class word, if they it says that after the class dot space the ANN is the best word fit in there. It is done by the multi-node probability distribution, and we added to the already generated stack. That's a sequence, and we decode it with our embedded characters, and it becomes our text. We have a this is our architecture, but it is generated by TorchWiz. I have not written it. It's a huge actually. This is a huge map of our ANN architecture. It's generated by TorchWiz software. It's a nice software, but it does not include all of the layers, but it is very useful. We have a transformer architecture from scratch. It is a generated pre-trained transformer from scratch. It's not. We have not used OpenAI. So this is our. We have sequential layers. So we have used our PyTorch neural network model. We have 6 sequential layers. We have a model, multi-head and head in the multi-head and head layers. If we have a CD, we have the key query value pairs, and it has a formula in the paper. You can see it's a trivial formula, and these are the linear layers. And data generation with less training. This is this is generated with less training. It's just a stack of words, a stack of characters, not with anything, no meaning at all. And the iteration step is the initial steps of iteration. And we have set the dropout to open for, and it is after the training, but the dropout size is open for. The words has no meaning. It does not mean anything at all. And have optimization algorithm use AMW and our RMS probe above. For example, at these positions, we want to find the minima of the or the maxima of the function. That's not possible. So we find the local minima or local maximum of the function, and we use the RMS probe optimization algorithm for this particular problem. And AMW is also considered. We have used lots of matrices. If you see scalar, vector, matrix, tensor, everything in artificial neural networks is a tensor object. You can see the tensor flow. That word comes from tensor. You know, tensors are very important. Have you done lots of matrix operations? It is trivial, you know, but it's not difficult. The determinant is the area between the vectors. You know, linear algebra, it's very important. It's the language of the quantum computing at the moment. So we have to use it too much. We have used a matrix dot product in here. Like you see the at weight times the values pairs in the out equals. So it's used a lot in this paper. So activation function is our sigmoid activation function. We have activation functions. Another activation functions in here. This is the transfer function, activation function, and it stores our output. This is another. I guess it was from the loss function. We have another tangent H function, activation function, and ReLU, rectified linear activation function. It's used a lot in this modern networks. I have not changed the activation function. It's because we have used a PyTorch neural network model. It has used itself. Other like ReLU, we have another activation function is also max out used, and feed forward. We have feed forward, and these are all by the PyTorch neural network model. What these are required steps for the artificial neural network base. We have it's a very important feature because we adjust the range in each iteration. So we have loss function, cost function. The generalization of the loss function is our cost function. It's gradient descent optimized parameters. And this is our error function. This is a simple examination of the mean squared error. If you want the implant output difference on squared and the sum it takes generalization. And logical neural networks, these are formulas mostly used in the current modern neural networks. Convex of the function, is it going upwards or downwards, gradient descent of the function. These are very important features of using in neural networks, minimum, maximum. I've talked about it. And these are the basic mathematical features used in these problems. Calculus is also used. These are our plots from TensorBoard, extracted from TensorBoard during the learning. If you see in the top histogram, there's a sort of noise, but at the end of the histogram, you will see that it is clear after optimizations. Underfitting, overfitting is very important issue. This is most educational, these graphs. Underfitting, overfitting in classification problems. If you see it, that's very unclear to many. And confusion matrix. Actually, the confusion, it's very difficult to process the confusion matrix in transformer architecture problems and the TensorFlow. We have not used TensorFlow, but it's very efficient. We have used PyTorch. It's good for quickly making your software. It's good for educational purpose, and it's pure Pythonic. But TensorFlow is backed by C++. It's efficient. It will be used in the real software. Keras is a high level of the TensorFlow. I have not used it. These are very good differentiation. I've taken it from Simple-Learn. Those are very good graphs. I will skip for a time is going. And the processing power. We need Q.GPU for everything in working with artificial neural networks. If you compare it with a CPU and the GPU, we have matrix operations supported. Okay. In the CPU, we have control unit, artificial arithmetic logic unit, cache, L-bit, L2, L in caches, registers, general purpose registers, dynamic RAM, static RAM, lots of things. Still are actually for the general purpose computing. But in GPU, the only problem is the display. You have to graph something on your display. So it is kind of ASICs, application specific interface, but it's not ASIC. It has orientation, so it has very good support for matrix multiplication. And in the artificial neural networks, we only work with matrices. This is 70% of the artificial neural process. Historical, if you see the graphical processor, we have GPG, we have GP, general graphics programming. Yeah, graph on GPU. It's in the OpenCL. You see, these are very important steps of the history of the graphics processors. And CUDA is introduced in 2007 in the graph. And if you see the CUDA parallel computing architecture, it supports C, C++, OpenCL computing, force-running Java, Python programming languages. And another comparison of the and this is a architecture. And also another picture. This is very important. CUDA architecture. We have constant. This is the architecture of CUDA GPU. This we have constant memory, global memory, local memory, threads, registers, shared memory, and those are in blocks. And this is what makes CUDA GPU very special. It's very efficient for our neural networks processing. The architecture designs for GPU and supercomputer. This is the last topic, I guess. We need supercomputers. I have worked recently in IBM's artificial intelligence course, and we did not use GPUs for training the or even neural network models. It gives us lots of CPU power. I don't know. I don't think how it's efficient, but lots of CPU power. It gives you 8 CPU in distributed parallel computing. It gives you 8 CPU. And that's somewhat equal to the Google Collapse, maybe T4 architecture. So supercomputers, even if it has CPU or GPU power, are very important. We need supercomputers. I have trained all of the work in this laptop in the picture. It has a Core i7 Intel 2 cores, 4 logic processors, 3.5 average oscillation frequency, 30 DRAM. And it is there. Storage is not important, but if you see the internal graphics is 128 megabytes. It's very low. It actually does nothing. So it's very important. And thank you for watching my presentation. And this is the graph. This is the optimized graph. If you see the histogram, at the weight are oriented on the 1.7. So this is not the latest. I had decreased it to 1.5. The validation loss was 1.5. So this is a smooth graph of the decreasing the validation loss. So this text is the last with the best weights, and it has been generated. If you see, we can find some sentences with meaning. And those are all in Tolstoy style, and those are all generated by our custom from scratch written gender pre-trained transformer model in PyTorch. Thank you very much, and if you have any questions, I like that.